All right, let's dive into what is arguably the single biggest quest in all of modern physics: the search for a theory of quantum gravity. You can think of it as the hunt for one single ultimate rulebook that explains literally everything in our universe, from the absolute smallest particles to the biggest galaxies you can imagine.
So, the whole thing really kicks off with a question that sounds like it's straight out of a movie. What happens when the most powerful, most successful ideas in all of physics go head to head? Because for about 100 years now, our entire picture of the universe has been built on two incredible theories that just flat out refuse to work together. You see, on one side, you've got general relativity, which is Einstein's masterpiece. It's our rulebook for everything big: planets, stars, galaxies, you name it. And on the other side, you've got quantum mechanics. That's the rulebook for the teeny tiny stuff, the strange, unpredictable world of atoms and all the particles inside them. And here's the thing, in their own territory, both of these theories are perfect. They work flawlessly. So to really get why they clash so spectacularly, we need to take a quick peek at what makes each of these pillars of physics so amazing all by itself. Okay, so first up is Einstein's big idea. He imagined that gravity isn't really a force pulling us down. Instead, he said that space and time are woven together into this four-dimensional fabric he called spacetime. And big, heavy things like planets and stars actually bend and warp this fabric. So what we feel as gravity is just us moving along those curves. It's smooth, it's elegant, and it describes the universe on the grandest scale beautifully. But then, things get weird. Because if relativity's universe is this smooth, continuous sheet, the quantum universe is more like a pixelated video game. Down at the smallest scales, everything comes in these little distinct packets, or quanta. You can't ever know exactly where a particle is, only the probability of where it might show up. It's a fuzzy, bizarre world built entirely on chance. Now, for most of human history, this wasn't really a problem, right? Physicists just used one set of rules for big stuff and another for small stuff. But there are a few places in the universe where the very big and the very small are forced to meet. And in those places, our entire understanding of physics just completely shatters. These places are called singularities. The two most famous examples: the superdense point at the very center of a black hole, and the entire universe crushed down into a single point at the very first instant of the Big Bang. In these spots, you have a huge amount of mass, that's relativity's territory, crammed into an unbelievably small space, which is quantum mechanics territory. And this is where the crisis hits. When you try to use our current laws of physics to describe what's happening in a singularity, they just stop working. The equations spit out nonsense. It's like a giant flashing error message from the universe, telling us that our rulebooks are missing a page. Now, the fancy term for this problem is non-renormalizable, but all that really means is when you try to jam the equations of quantum mechanics and gravity together, the math breaks. It gives you answers like infinity, which is just a polite way of saying, I have no idea. The universe is telling us in no uncertain terms that we can't just tape these two theories together. We need something completely new.
And that is what launches us on this epic, heroic quest of modern physics: the search for a unified theory of quantum gravity. The goal is nothing less than to write that missing chapter, to find the single set of rules that works for everything, everywhere, no exceptions. Now, this is not an easy problem to solve. Not at all. I mean, to give you some perspective, scientists are exploring at least 16 different major approaches to this. It just goes to show you how massive and mind-bending this puzzle is. It's something that has stumped the absolute greatest minds on the planet for decades. And while there are a lot of ideas floating around, two of them have really emerged as the main contenders. You've probably heard their names before: string theory and loop quantum gravity. They both paint these incredible new pictures of reality, but they start from totally different assumptions.
So let's start with the famous one, string theory. It says that if you could zoom in way, way down on any particle, an electron, a quark, anything, you wouldn't see a little dot. You'd find a tiny vibrating loop of energy, a string. And just like a guitar string can play different notes, the different ways these tiny strings vibrate give us all the different particles we see. In this view, the whole universe is basically a grand cosmic symphony. Loop quantum gravity, or LQG, comes at the problem from the other direction. It doesn't worry about particles at first, it focuses on space-time itself. It says that the fabric of reality isn't a smooth, continuous sheet like Einstein thought. Instead, it's made of these tiny, indivisible chunks, or loops. Think about the pixels on your screen. From far away, it looks smooth, but if you get close enough, you see it's made of individual dots. LQG says that's what space and time are really like.
Okay, so what happens when you start to really think about what these ideas mean? Well, you get some of the most bizarre, absolutely mind-bending predictions in all of science. We're talking about things that turn even black holes into something stranger than we ever imagined.
One of the very first clues came from the legendary Stephen Hawking. He realized that if you apply quantum rules to the edge of a black hole, something amazing happens. See, empty space isn't really empty. It's fizzing with pairs of virtual particles that pop into existence and then disappear almost instantly. But right at the edge of a black hole's event horizon, one particle can fall in, while its partner escapes out into space. And that escaping particle looks like radiation. It means the black hole is slowly leaking energy, and over trillions of years, it can actually evaporate and disappear.
This incredible discovery led to a brand new concept, the Hawking temperature. It means that black holes aren't perfectly black. They actually have a temperature, and they glow, even if it's unbelievably faint. This is just a perfect example of why this whole search is so important. By just starting to combine relativity and quantum mechanics, we discovered something totally new and unexpected about how the universe works. And look, this isn't just about some weird math on a chalkboard. The search for quantum gravity is really about answering the deepest, most fundamental questions we can possibly ask about the universe and, our place in it. If we find this theory, it would be like getting a key to the universe's most secret rooms. We could finally figure out what happened in that very first instant of the Big Bang. We can know what's really going on at the center of a black hole. We might even find out if space-time itself is fundamental or if it's just an emergent property, kind of like how the feeling of wetness emerges from a bunch of individual water molecules. This is our only shot at telling the complete story of our cosmos. And when it comes right down to it, the reason we do all this is captured perfectly in this quote. The goal isn't just to make predictions. It's to find a clear conceptual framework that actually helps us understand all the crazy, amazing things we see in nature. This quest is nowhere near over. We don't have the experiments yet to tell us which of these wild ideas is the right one, or if maybe the answer is something we haven't even thought of yet. But the search goes on, pushing the very limits of what we know and can imagine, and leaving us with that one huge, tantalizing question. Will we one day actually hold the ultimate rulebook to reality itself?